Hi ho, this one's all about power. It's the rate of doing work. So work is your force times displacement. Remember, they're both vectors. They have to be in the same direction. But power is how quickly you can do the work. Okay? For example, I can do the same work as that maybe what a forklift could do. But what's different is the forklift can do the work much faster than what I could. Okay? So power, if you have a more powerful engine, that means it can work faster, or it can do the same work in less time. Okay? So a couple ways to look at this. One is just the energy, and work causes a change in energy, so it could be your energy per time as well. Okay? But also look over here, guys. This is a displacement per time. Remember what a displacement per time is? Well, that's a velocity. So another way to find power is how hard you can push on something and how fast. If you can push on something and the faster you can move that'd mean you'd be more powerful because the displacement per time is velocity. So in general, it's just your work per time, how quickly you can work, or the amount of energy completed in a certain amount of time, because the energy completed is the same as the work done. All right, well, here we go, guys. The unit for this is watt, after old James Watt. So James Watt invented he didn't invent the steam engine, but what he did is he put it to use. He made kind of like a tractor-like device with the thing. Back in the day, horses did all the work. So when you make something, you're trying to profit off it. Otherwise, you don't have any food to put on the table. So what James Watt did is he said, I think this thing's going to be useful for people to get stuff done. So rather than having horses to feed and clean up their poop, well, you can just feed a steam engine some wood or coal or something to boil some water, and that steam engine can do the same work as so many horses. So James Watt, he set up the experiment to say, okay, so a horse has about this much power, and this is what my machine can do compared to a horse, or how many horses it is. Well, today what we call it horsepower, we do it in watts. Watts is a joule per second. Okay, a joule, if you remember, is a newton times a meter is a joule. So you take that newton meter, a joule, divided by the time in seconds, what's joules per second, or watts. And if you were able to produce 746 watts or joules per second, that would mean you have 1 horsepower. Okay? So one day this week, we're going to look at how powerful you guys are. You're going to do some exercising to find out what your power is and compare it to see if you're a horse, more than a horse, or less than a horse, of course. Okay? Well, here we go, guys. Let's do some examples of how to find the power done by something. Woo! Okay, guys, that dude, he's doing it again. 1,250 joules of work in half a second. Well, that's quick. 1,000, I have to count pretty slow for that to be a half a second. So to find the power, it's that energy per time. So it's the 1,250 joules. Remember, the way you found the work is by weight or force times distance moved. It's force times distance, but whatever that weight is, that's the force you're pushing up with to move that. So the 1,250 divided by a half a second, which means times 2. Whoo! How many horsepower is that, everybody? Because remember, 1 horsepower is 746. That's a few horses. It doesn't look like it by looking at the dude, but that is, in fact, a 3.35 horsepower dude. We're going to see how your horsepower compares to this dude over here to see if you can produce 3.35 horsepower. Okay? So let's do another example. That was so much fun the first time. So now this one might be a little more realistic. He's running into the ceiling, I think. Put some holes in the ceiling. Look at that. Bam, right into the ceiling on that one side. So this is only a 500 newton, but he is lifting at 2.5 meters, so that's a bunch of work, but in 1.5 a second. He's either tired or he's not as powerful as the last person. So find the work done. It's your 500 times 2.5 divided by 1.5. That's all you got to do. Your 500 times 2.5 divided by 1 is 833 watts. So it's not as impressive or as powerful as the other fella. Still not bad. That's more than a horse, guys. All right. Hey, so one exercise you could do is you could run some stairs. So here's a girl that weighs 500 newtons. Hey, pop quiz, what's her mass? 50. Nice. It's about 50. She's about 50 kilograms of mass. So on planet Earth, she weighs 500 newtons. Takes her 50 seconds to get those stairs that are 18 meters high. What is her power output vertically? Well, the reason it says vertically is because if she weighs 500, she has to push on each stair upwards with 500 newtons to go up, right? So that means that's how we know how hard she's pushing on the stair. It's the same as her weight. So she's pushing upward with 500 over 18 meters. So the work is 500 times 18, but divided by that 50 seconds. Alrighty. So 500 times 18, cross off a 0 there. 50 times 18, which is 100 times, not 250 times 9. Anyway, it's 180 watts, guys. So that might say, hey, that's less than a horse. Yep, it is. But this person is working for 50 seconds, not simply a half a second or 1.5 seconds. Turns out, guys, we all have a maximum horsepower for about 4 seconds. Probably the same with horses, too. So after 4 seconds, you depleted some of that sugar, that glucose in your muscles, and then you don't have quite the same power anymore. So this is way after 4 seconds, and you guys have done some stairs before. You notice it's easier on the first ones, it's harder on the last ones, okay? So that may not seem much like 18 meters, but in terms of feet, that's like 60 feet high, guys, okay? Alrighty. Ooh, how many calories did she burn? This could be interesting. So figure out how much work she needs to do to burn off maybe that donut they had for breakfast. Okay? So let's talk about what calories means, because that's an American term. Non-Americans tend to use not calories, but joules, like the kilojoules on their candy wrappers and their food wrappers and everything instead of calories. Americans, we like to use calories. Okay? Turns out a food calorie, a calorie by itself is not a lot of energy, guys. It's the amount of energy it takes to raise 1 little milliliter of water by 1 degree Celsius. It's not a lot. So we talk about kilocalories, or into the thousands. And when you do a big C, that's a food calorie. A food calorie is a kilocalorie, one and the same thing. So 1 kilocalorie is their food calorie is actually 4,186 joules. So on your food packaging, they don't have joules if you go up to the Great White North, even though recently it came down to meet us this last week. They have kilojoules, not joules, because that's a lot of numbers you're going to have to put on something. So if something's 100 calories, well, that would mean, and then that's, 418,600 joules. And so they use kilojoules. So in kilojoules, that's 4.186. So the moral of the story is that 100 calorie food calorie thing, if you look at the up in Canada, what that's going to read, it's going to read 19 kilojoules of energy. So it looks like it's pretty energetic, but remember, there's about the number's 4 times larger than this, even though it's the same energy. So keep in mind that's a conversion we're going to have to use to figure out how many stairs you'd have to do to burn off that Krispy Kreme. Alrighty, so work, change in energy. It causes a change in energy. So she's gaining a lot of it, gaining 9,000 joules of energy, potential energy. Okay, so that's 9 kilojoules, if you see kind of where I'm already going with this thing. Okay, so that's the work to get up there. Now if you want to change that into calories, well, it's 9,000 joules divided by the 4,186 joules per kilocalorie. 2.15. Oh, that does not look promising, guys, because that Krispy Kreme, that's not even a bite. Okay, but here's the other part of it, guys. We're only about 10% efficient, okay, roughly. So that means she actually burned more energy than that, because 90% of the energy that she used actually was given off as heat energy. That's how our bodies work. Okay, we like cooler temperatures than your body temperature because we're metabolizing things. We got to get rid of the heat energy. So that means if we're only 10% efficient, she actually burned 21.5 calories. And only 10% of that, because it's 10% efficient, went into use for work or stored potential energy of the 9,000 joules. That's what did 2.15 calories. 2.15 food calories or kilocalories is the same as 9,000 joules. So only this is the 10% out. So that's better news, but that's like a third of a banana. So she's gonna have to make 2 more trips just to burn off the banana that she had for breakfast. Okay? So sometimes exercise is a means to lose weight. It can be helpful, but that's not the easiest way to do things. Okay? Because that was just one time. Sure, she can do it more, but do it 5 more times, and now she's gone up to a whole 100 calories. So it does add up, but there you go. Alrighty. So that's a quick example of how you can figure out how much work you would have to do just to eat that donut. I know it's a tasty donut, but in the end, it's probably a lot easier just not to eat the donut. So does it matter how fast the work is completed? No. Turns out it does not. It's just the amount of work done. So if you can do it faster, you've just burned off that 21.5 calories faster than somebody else. It's still the same energy or work to get up there, assuming you're the same size. Okay? So the reason to do things faster is because you got other stuff to do, or you have a lot of work to do and you just got to get it done fast. So it turns out it's the same work whether you run up the stairs, you crawl up the stairs, roll up. I don't know if I ever seen anybody roll up the stairs, but that could be interesting. But it's the same work done. But the more powerful somebody is, that means they can do it faster. And if they can do it faster, they might be able to get more done in the same amount of time. Hence, that's why you buy the big engines and everything, the big tractors. They can work faster. Okay? They can do the same work, but a lot faster because there's probably a lot more work to be done. Okay, and the sun's going down. Alrighty, some quick sample problems here. We've got 3 minutes to be done, so we can get it on the old YouTube and maybe we'll be famous. How much? Okay, they're individual ones. Let's just jump right to the. Here we go. 20 newtons times 5 meters. So we don't have to know the 2 kilograms because we're not going up and down. That's just the work done. 20 times 5, that's 100, right? Simple stuff. 2, how much power is needed to do that thing in 7 seconds? Well, that's 100 divided by 7. 14 watts. Not a big cart. Okay? So power is the rate of doing work, how quickly you can do it. 3, we got some other girl, only 30 kilograms. This is a wee one. So she's like a 65 pounder. My daughter's bigger than that, and she's 9 years old. Takes 45 seconds to climb 24 meters. So 300 times 24 divided by 45 is, bam, 160 watts. Not a horse, less than a horsepower, but still, hey, there it is. That's a pretty big climb, 45 seconds or 24 meters. Yikes. That is a big climb. Alrighty, guys, that should be it for the power. And have a wonderful one. Got it in with a bonus time of 1 minute and 40 seconds almost to spare. Alright, I'll shut my mouth.